All right, we're presented with these four materials. All right, these four materials, and they say they want us to use these materials in a Wittig reaction. A Wittig reaction. So this is kind of a little silly way to ask this, but because really you wouldn't throw all four of these in at once. You have to know what starts. So in a Wittig, you should know in your head, what does Wittig do? It takes a carbonyl and turns it into an alkene. C double bond O to a C double bond C. Right? So here are the four reagents that are in a Wittig. The problem I have with this is that you need to know that this one and this one, the triphenylphosphine and the alkyl halide actually react first. So triphenylphosphine, right, like below nitrogen, has a lone pair. So it does an SN2 reaction, right? Does an SN2 reaction, gets this reagent, they're not threes there, sorry about that. There's now a plus charge on our phosphine. We have this Br minus. Let's number these carbons. 1, 2, 3, 4. Right? And we've done one of these kind of things. We've looked at this in a worksheet before, actually, if you remember. I think it's maybe this exact example. So the next reagent we're going to use is this N-butyl lithium, right? So it's the organolithium. So you should recognize this to mean that means lithium plus C minus, right? It's like a carbanion. And so what's that carbanion going to do here? It's actually going to deprotonate, because if you remember what a Wittig reagent is, a Wittig reagent needs to have a negative carbon on this carbon attached to the phosphorus, because this is the carbon that's going to add into the carbonyl. So what happens? It's an acid-base reaction. Again, I would present this to you in a much more deliberate manner. I wouldn't throw all these things at you at once. So this is deprotonation. Plus, minus. You also made, so there's 1, 2, 3, 4. You made butane as well, right? That was from the lithium piece. So there you have, and you also would make lithium bromide, right? If you're worried about balancing everything out, there it is. Actually, this, I added a carbon. Whoops. All right, so you'd have this. So this carbon had 2 hydrogens on it. Now it has 3. We took that hydrogen from 1. So now this is my nucleophile, which is going to react with my cyclohexanone and do the Wittig reaction. So now we're going to actually do the Wittig reaction. This adds in there. Right? We do the addition. We make a tetrahedral intermediate. And this, of course, is a special tetrahedral intermediate. Because this one's going to form a cyclooxetane? Oxetane? That's called. Doesn't really matter. It's going to form a 4-membered ring. So you have the product of that. Of course, phosphorus, because it's lower on the periodic table, can expand its octet. So now it has 5 bonds, but we're okay with that. We're going to settle that in our organic brains. And then essentially what happens, this whole thing breaks down. Right? And of course, I've been lazy here because I forgot to add, we number our carbons. 1, 2, 3, 4. 1, 2, 3, 4. Right? Add those things in. And we end up with this as our product. Right, the alkene. Now, be careful. This is not exactly like the problem you're given. I did change one little thing. So make sure when you're going back through this, if you put this answer in, you will not get the points. Go back through and check out your 4 starting materials. So they're telling us in this reaction, it takes 4 steps. In each reaction box, place the best reagent and conditions provided. You can use reagents more than once. So, I mean, really you could do this without having the boxes, but let's take a look. Let's take a look at essentially at what we need to analyze this from the beginning. All right, so I'm going to number 1, 2, 1, 2. Why did I do that? I'm just looking at this, looking at these things, right? So we went from a ketone to an ester. I know esters from things I've done I can lose this piece, right? I can add things in and lose that piece. A lot of times, if I do things reactions with esters, though, they turn into alcohol. So a guy may be thinking, well, a lot of times where I can add carbons, the final product's an alcohol, actually. So that means you need to think, well, how do I turn this alcohols into ketones? So maybe think about oxidations, a couple of those different things. Now, one thing you need to think about when you have esters, right? So you should all be, I say alcohols, I see in carbonyls, and we're adding carbons, right? We're adding carbons. You should all be thinking what kind of reagent? Grignard reagents, right? That's our classic way to add carbons. But you should also think, when I have an ester though, and I react with Grignard, how many Grignards do I add to esters? I actually never just add 1, I always add 2. And why is that? Because esters have a good leaving group, right? When that first Grignard adds in, I make a tetrahedral intermediate. And we make a tetrahedral intermediate, we ask ourselves, do we have good leaving groups? And if you do, that leaving group leaves. So the problem with esters is, esters always get 2 Grignards added. But if you look here, I'm only adding 1 new thing. So I have to do something to this probably first before I get to here. What could that be? Right? So if I take 1 step back here, I could probably assume that this was what? It was probably maybe this alcohol. Now somebody might say, well, how did you know that? Well, just looking at the starting materials, right? I know I'm going to need to go through some sort of alcohol, right? Because I'm going to need to add carbons, right? That's kind of the thing we've been doing with adding Grignards, right? So where would this have came from? Well, this is the piece I want to add, right? Everybody can see that? And there's carbon 1 and 2. So what bond are we talking about breaking here? We're talking about breaking this bond, right? Everybody see that? Right, if we do the analysis of alcohols, we've done a couple times. So that means that we would have had this, right? Because there's an H here. We really ever draw it in. There's carbon 1 and there's carbon 2. And then our Grignard would be it doesn't have to be Grignard. It also could be an organolithium, right? That's the same difference. It's the same thing, carbanion. And now the question I have for you, do you know a way to turn an ester? Can you turn an ester into an aldehyde? What reagent does that? Do you remember? What kind of reaction is this? Overall, what kind of reaction is this? We're going from ester to aldehyde. What kind of reaction is it? Oxidation or reduction? Does carbon 2 have more bonds to oxygen or less bonds to oxygen at the end? It has less, right? You're adding an H. So it's reduction. You only know 3 ways to do reductions. Sodium borohydride, which isn't reactive enough to react with esters. Lithium aluminum hydride, which is reactive enough, but it's going to turn into an alcohol. And then the last one is DIBAL-H. Remember DIBAL. So step 1 would be DIBAL, E, then H plus workup. That gets us there. Now we need to add this reagent, right? That'll get us to not quite there because we need to add H3O plus, H plus again, right? To protonate the alcohol. So you need to have the alcohol protonated in there. And then if we want to do this step, what do we need to have? We need to have chromium, right? Or you could say PCC would work too, but some sort of oxidizing agent, right? We're losing the hydrogen and taking that hydrogen off and oxidizing to that carbon. We're presented here with an imine and a carboxylic acid. An imine and a carboxylic acid. So we need to think about ways to turn, we need to think about how to make an imine. So we just need to recognize that this is an imine and what that might have came from. And then also, do we add any carbons? I think we add carbons through the nitrogen. I would say that's probably the first step. So if I take one step back, if I number these carbons, 1, 2, this came from this, right? Nitrogen piece is right there. So the other byproduct here, of course, must be some water. It's a condensation reaction. How do we take carboxylic acid and turn it into an aldehyde? That's kind of where we need to go from. Well, to make an aldehyde, all right, 1, 2, it probably came from an alcohol. Right? It probably came from an alcohol. 1, 2. How did I know that? Right? We kind of just got done talking a little bit about that. Why that's the case. So I have this alcohol, and I recognize that probably this aldehyde probably came from the alcohol. Just looking at, there's a 2-carbon piece here, and maybe one of the reactions you've forgotten, or we didn't cover very explicitly. There is a way to turn a carboxylic acid into an alcohol. So what kind of reaction is this? So you probably could figure this one out. What kind of reaction is this? It's a reduction, right? Taking carboxylic acid, we're not adding any carbons. What we're doing, we're adding hydrogens to carbon 2. Right? How many reagents do you know that do reductions? Well, you know 3. You know DIBAL-H, which is esters, and turns esters into what? Into aldehydes. You know sodium borohydride, which reacts with only ketones and aldehydes. And then your last one is that really reactive one, lithium aluminum hydride. So guess what? Lithium aluminum hydride is the one that can take a carboxylic acid and turn it into a primary alcohol. So moving forward then, we'd have step 1, lithium aluminum hydride. Step 2, you're going to need some H plus to protonate it if you make that tetrahedral intermediate. The next step, to get to that amine, guess what you're going to need to do probably? What do you think you're going to need to do? An oxidation, but you got to be careful. What kind of oxidation do you need to do? You need to take a primary alcohol to an aldehyde. You need to use that special one, PCC, the one that doesn't work as well, that stops at an aldehyde, so you got to use PCC. And then the last thing you do is you have this, and you're going to need some H plus as a catalyst to make this go. And that forms your imine.